To today's class on secret sharing schemes. So, today's class we shall essentially discuss about a very interesting technique of sharing secrets. So, it is also commonly referred to as the threshold scheme, and it is based on Shamid's secret sharing protocol, and which actually tells us how to share the secrets between a set of users. Okay. So, and we shall also discuss about how to initialize this scheme, how to create the shares, how to reconstruct the secret, and what is the essential security of the scheme. Okay. So, this is the broad aim of today's class. So, to start with, let us consider a problem. Okay. So, it is a combinatorial problem. So, consider that suppose there are 11 scientists who are working on a secret project, and they wish to lock up the documents in a cabinet, so that the cabinet can be opened if and only if 6 or more of the scientists are present. Okay. That means, there are 11 scientists who are working on the problem or on the project, and if and only if 6 or more of the scientists combine, then they should be able to understand the secret project, right. So, the questions which can come or arise are as follows, like what is the smallest number of locks needed. Okay. So, just think that it is kind of an we often apply interlocks to our doors, right. So, therefore, it is a similar kind of problem. So, the question which can arise is what is the smallest number of locks which are needed, and the other question is what is the smallest number of keys to the locks each scientist must carry. Okay. So, how do we essentially solve this problem? So, you see that the problem essentially can be visualized like this. So, there is a set like this, and suppose there are 11 members in this project, right. So, I am not exactly giving that, but suppose there are 11 people here, okay. And out of them, if 6 people combine, okay, if 6 people combine, then they should be able to understand the project, understand the secret. Okay. So, therefore, the question is what is the smallest number of locks that are needed. So, you can immediately compute that that means that the number of locks means what, that is if there are 11 people, what a possible solution can be like this, right. That is, you choose any 6 people, and for any chosen 6 people you keep a dedicated lock. Okay. So, that means the number of locks which are needed are the number of ways how you can actually choose 6 from 11, right. So, therefore, the number of locks can be computed to be this is equal to 11 choose 6. Okay. The next question is what is the smallest number of keys to the locks each scientist must carry. Okay. So, therefore, for that we have to understand that a given scientist, okay, can be a member of how many such groups of 6 people, right. So, that means you can see that immediately that if the group has got 6 people, a particular scientist will form a membership with how many scientists, with 5 scientists, right. So, there are 5 scientists with whom this particular scientist, say scientist A, can form a membership, right. So, therefore, if you leave out this particular scientist, there are 10 people apart from this scientist A, okay. And therefore, the smallest number of keys, obviously you can keep larger number than that, but at least you need these many number of keys can be found out by the number of ways you can actually choose these 5 people from the remaining 10 people. Okay. So, that means it is 10 choose 5, right. So, therefore, you can immediately calculate that the number of locks or the minimum number of locks which are necessary are 462, and the minimum number of or the smallest number of keys to the locks each scientist must carry is equal to 252. So, therefore, you see that even for a small problem which has got 11 people, and we want a scheme where 6 people, if they combine, they can understand or deduce the secret, then this kind of scheme requires a very large number of locks and keys, right. So, therefore, the objective of developing an efficient secret sharing scheme is to find out a mechanism through which you can actually divide the secret among say n people, such that out of them, if t people where t is less than n, if they combine, they should be able to find out the secret, but the scheme should be efficient, which means that the number of locks and the number of keys should be small, right. That means the computational overhead should be as minimal as possible. Okay. So, therefore, we formally define the secret sharing scheme. It is as follows. The goal is to divide a secret D into n pieces. So, there is a secret D which I would like to divide among n pieces. So, there is a secret D and I want to divide that into n such pieces. Okay. And the idea is that if out of them, if I can actually find out t such shares, that is di1, di2 and so on till dit, if I can find out t such shares where t is less than n, okay, then if t is less than n, okay, and if we can actually obtain these many shares, then you should be able to obtain or deduce back the secret. Okay. But if the number of shares is less than t, that is, it is even if it is t minus 1, then the information which is leaked about D should be ideally 0. That is, the adversary or rather the adversaries, if there are t minus 1 people who are combining, they should not be able to recover the secret. Okay. So, therefore, the knowledge of any t or more di pieces makes D easily computable, but the knowledge of any t minus 1 or fewer di pieces leaves D completely undetermined. That is, all possible values of D are equally likely. Now, when we are saying that all possible values of D are equally likely, we are actually saying that in an information theoretic sense. That means, it reveals no information on D. Okay. So, these kind of schemes are commonly referred to as the t comma n threshold schemes. That means, there are t players, if they combine out of these n players, they are able to deduce the secret, but if there are t minus 1 or fewer players or shares, then that does not reveal any information about the secret which is being shared. Okay. So, you can immediately understand that these kind of protocols or these kind of techniques can have varied number of applications, like one possible applications could be in distributed file systems, right, where you want a security as well. So, therefore, you know that if so many people combine, then you can actually deduce back the secret, but if it is lesser than that, then you are not able to deduce the secret, right. Right. See, consider this simple example, that is, suppose there are consider some binary or rather vectors like x1, x2 and so on till xn. Okay. So, consider this function, that is, if I take the bitwise XOR of these like x1 XOR, x2 XOR, xn. Okay. So, you can consider that all of them are 1 bit values. Okay. That is, any xi is a member of 0 or 1. Okay. So, consider this XOR sum. So, if this XOR sum is x, that is, x is equal to x1 XOR x2 XOR so on many xn, then you see that in order to find out the value of x, we actually require n values, is it not? So, if there are n minus 1 such values which are being obtained, then what is the information leakage about x? It is 0, right, because even if you do not have one such contribution, then the value of x can be either 0 or 1 with the equal probability, right. So, therefore, this is an example of an n comma n threshold scheme, right. So, this is an example of an n comma n threshold scheme. So, now more interestingly, we want to actually find out a technique which is lesser than that, that is which is actually a t comma n threshold scheme. Where t is less than n. Okay. So, how to devise a mechanism which is like this. Okay. Do you understand the problem? Okay. So, for this, first of all, let us consider an important lemma. Okay. It says that let n comma t be members of natural numbers and L is lesser than equal to t. Okay. So, that is value L which is lesser than equal to t. Also, let x I y I belong to Z. So, that is the basically the congruence set, that is again it is comprising of Z and Z p Z, that means that it is the congruence set which is generated by P, that is where P is say a prime number, you can actually generate from 0 to P minus 1. Okay. So, consider that x I and y i's which are actually members from 0 to P minus 1, and let 1 is less than equal to I is less than equal to L, where the x i's are pairwise distinct. Okay. So, the x i's are pairwise distinct, and what the theorem says is that then there are exactly p to the power of t minus L polynomials, okay, and the polynomials are given like this. So, there are exactly p to the power of t minus L polynomials, and the polynomials are given like this. Okay. So, which means that the polynomials, the indeterminate is x and the coefficients or polynomials are belonging to this set, that is they are members from 0 to p minus 1. Okay. And the degree of this polynomial or these polynomials is less than or equal to t minus 1. Okay. So, what are the possible values of the polynomials? So, polynomials could be like b0 plus b1 x plus b2 x plus so on till x to the power of t minus 1, that is the degree, right. Is it not? So, that means it is squared. So, this is t minus 1, right. So, this is a possible polynomial, right, and what are these coefficients? Any b0 or any bi for that matter belongs to from 0 to p minus 1, that means it belongs to this particular set, right, and it says that there are exactly p to the power of t minus L polynomials with this degree and etc., such that with b of x I being equal to y I for all I varying from 1 to L. Okay. That means that the polynomial satisfies this equation, that is if you take x I, if you take x1, x2 and so on till xl, then all of them are equal to, I mean like b of x I, b of x1 is equal to y1, b of x2 is equal to y2 and so on till b of xl equal to yn, right. And how many such polynomials can we construct? There are exactly p to the power of t minus L such polynomials which you can construct. Okay. Now, why so? So, in order to understand that, you consider the Lagrange's interpolation formula. Okay. So, the Lagrange's interpolation formula says that if you have got a polynomial bx which is constructed as follows, you take a sigma over yi where I varies to from 1 to L, and then there is a product from j equal to 1 till j not equal to I, okay, till L, and you take x j minus x divided by x j minus x I. Okay. So, this polynomial will satisfy b of x I equal to y I for all such i's which lies from 1 to L. So, that means this is what the Lagrange's interpolation formula says. That means, it is kind of like if I have got points like x 1 y 1, x 2 y 2 and so on till x l y l, then I can using the Lagrange's interpolation formula, I can actually calculate or compute this polynomial for which all these relations are satisfied at all these L points, right, which means that there exists one such polynomial which satisfies all the L values, right. Now, what we have to show actually is that there are p to the power of t minus L such polynomials for which this holds, right. Now, in order to understand little bit or appreciate this algorithm or rather this interpolation polynomial, you can consider the case where L is equal to 2. Okay. So, consider the case where L is equal to 2. So, that means your B x will be I varies from 1 to 2 and this is y I and this is x j minus x, x j minus x I, j equal to 1, j is not equal to I and it varies till 2, right. So, what is that? That means that this is equal to y 1 and that will be multiplied by x 2 minus x divided by x 2 minus x 1, right, plus y 2 and that is multiplied by x 1 minus x divided by x 2 minus x 2 minus so that is x 1 minus x and that is x 1 minus x 2, right. Is it correct? So, now you see that in this polynomial, if you write b x and you compute it at the value of x being equal to say x 1, then if you substitute here x 1, then this x 2 minus x 1 by x 2 minus x 1, this value becomes equal to 1, right. So, what is this? This is y 1 plus y 2 multiplied by this value goes to what? Goes to 0. If you plug in here x equal to x 1, then this term goes to 0. So, we have got only y 1. Now, what about if you compute this at the point x equal to x 2? This is similarly equal to y 2 because now this goes to 0, right. So, you see that this interpolation works for L equal to 2, right. So, similarly you can actually prove that this holds for any L also. So, therefore, you can actually say that your B x, so again writing down this B x was equal to y I. So, for the general case was equal to j equal to 1, j not equal to I equal to 1 to L, okay, and this goes to j, this is x j minus x divided by x j minus x I, this was the original formula, right. So, let us compute this value of B x at the point of x equal to some value say x k. Okay. Let us compute this value of B x at the point of x equal to x k. So, that is equal to, we again take this sigma y I from I equal to 1 to I mean and this is I, say suppose I is not equal to k, okay, and this varies from 1 to L and then you have got y I and then pi j equal to 1, j not equal to I L x j minus x divided by x j minus x I, okay, plus the value when this is equal to k. So, that is y k and the product term has got x j minus x k divided by x j minus x k for all the terms, right. So, that is j equal to 1, j not equal to k running till L. Is it correct? So, you see that for all these things this is what? This is 1, right, and for all these things if you see that one of the terms will actually have x j, right. So, which means that this product will go to 0 because there will be one such case where x j minus x j will occur, right, and therefore, this will go to 0, this particular thing will go to 0, this will go to 1 and therefore, you will be remained with only this point y k. Okay. So, therefore, this holds for any k, and therefore, for all the L values the Lagrange's interpolation formula indeed gives us one such polynomial, right. Now, what we essentially have to kind of also argue that according to the theorem that there are p to the power of t minus L such polynomials of degree less than equal to t minus 1, where all such all the results hold, right. So, for that we have actually to go little bit into matrix algebra. Now, we also seek to calculate the number of such polynomials. So, let this be such one polynomial, and we have already seen that this is the form of the polynomial, right, that is sigma j equal to 0 till t minus 1 b j x to the power of j, where each b j, that is each coefficient belongs to z p z, that means it is from 0 to p minus 1, and for all j all such j's from 0 to t minus 1, right. So, therefore, if I know that b of x I is equal to y I, okay, then for all these values we can actually write them in this matrix notation, is it not? That is we can always write this in this matrix notation, because you know that all these are essentially polynomials. So, therefore, if you consider the first one, okay, that is you take x I, you just take b of x 1 is equal to y 1, that is this particular thing, that is 1 into b 0 plus b 1 x plus so on till b t minus 1 x 1 t to the power of minus 1, okay, is equal to y 1, right. So, all these L equations are written in the form of a matrix, right. So, therefore, now the question is that what is the, so therefore, this is this matrix notation clear, right. So, the question is now that this is the coefficient matrix, and this coefficient matrix we can study a little bit. Okay. So, this is actually commonly known as the van der Mondes matrix, okay, and its determinant is given by this thing, that is it is the product of x I minus x j, where I and j runs from 1 to L. Okay. So, you see that the determinant of this van der Mondes matrix is given by this product x I minus x j, where I and j runs from 1 to L. Okay. So, you note that if x I and x j are always distinct, that is they are never same, that is all the x values are distinct. Okay. So, that means that if that this value, this is a non-zero determinant, okay, and if the determinants are is a non-zero value, so the rank of this matrix is actually L. Okay. So, therefore, the rank is L. Okay. For this matrix the rank is L, and this implies that the kernel of the matrix, okay, going back to your matrix algebra classes, kernel of the matrix has rank t minus L. Okay. So, therefore, the number of solutions of the linear system, that is a linear matrix system, is actually p to the power of t minus L. So, you can just consider a special case, if your t and L are same, right, then how many such solutions are there? There is exactly one solution, right. That is when your t and L are exactly equal to each other, then you have got exactly one solution to the linear system. But as long as your L is, I mean your t is greater than L, you have got more than one solutions, is it not so? Okay. So, that means that there are so many matrices, and this is a very important and interesting observation and result which is used in the Schmidt's secret sharing scheme, right. So, this proves the first theorem, or the first lemma, that is there are exactly p to the power of t minus L polynomials of degree less than equal to t minus 1, which actually satisfies all the relations, all the L relations, all the L pairs x 1 x 2 and so on till x L y L, right. So, therefore, consider a special case when t is equal to L, there is one and only one such polynomial for this, for which this holds, right. And next we will discuss how to use this idea for solving the secret sharing problem. So, for that let us consider this initialization. What the dealer does is that the dealer chooses a prime number p, where p is greater than or equal to n plus 1, okay, and non-zero elements xi belonging to again 0 to p minus 1, and I is varied from 1 to n, which are always, and note that all these values of x are actually pairwise distinct. So, this pairwise distinctness is because we wanted the van der Waals matrix to have a non-zero determinant, right. So, therefore, that all of them are pairwise distinct, and the xi elements are therefore the least non-negative element in the residue class. So, this is the residue class of z p dash p z, and it is the least non-negative element. So, that means it varies from 0 to p minus 1, right, and the dealer publishes these values of xi. So, therefore, these values of xi are actually published by the dealer. So, that is the basic initialization phase which is being followed. So, therefore, the initialization phase of the secret sharing scheme comprises of generating the values of. So, basically the first thing is that you need a prime number p, okay, and then you need to find out values like x 1 till x n such that all xi's are actually from 0 to p minus 1, right, and these values like x 1 to x n are actually published by the dealer. So, now we have to prepare the shares. So, what is the share, how is the share prepared? So, let that there is a secret S which I want to share, that is in order to preparing the share, suppose the secret is some value S which again lies between 0 to p minus 1. Okay. So, what the dealer does is the dealer secretly chooses some coefficients of a polynomial. Okay. So, what the dealer does is that the dealer chooses, okay, secretly aj, where aj varies from 0 to p minus 1, okay, and constructs a polynomial. So, he constructs a polynomial of this nature, that is a x is given by s which is the constant plus sigma of a j x to the power of j, and j is being varied from 1 to t minus 1. So, this is the polynomial which the dealer creates secretly. So, what the dealer does is that it chooses these coefficients secretly, okay, and adds or rather keeps s which is the secret as the constant of the polynomial, right. And then what the dealer does, what is the degree of this? The degree of this is lesser than equal to t minus 1, right, depending upon your aj, because your aj's can be zeros also, right. So, therefore, the degree is maximum equal to t minus 1. So, the degree of this polynomial is lesser than equal to t minus 1, right. So, now the dealer computes the shares. So, the dealer computes the shares by calculating all the L values like y I by calculating the polynomials at I point. So, therefore, these could be like I is varied from 1 to n. For all n values, it creates n such shares. Okay. So, takes 1 x 1 for all these x 1 values, x 2 values, and so on till x n values, it creates y corresponding y I values. So, what now the dealer does is that to all the share members, right. So, suppose there are n share members, to the n share members it communicates y 1, y 2 and so on till y n. So, all of the dealer actually takes this and communicates this to all the n users, right. So, now you know that the secret is actually the value of a 0 of the polynomial a x, right. And what we have to understand is that if t members of these players combine, then they can actually compute the corresponding constant term, because the constant term is the secret, right. Is it clear? So therefore, what the t shareholders do is that they collaborate, right. So, they basically come together, and without loss of generality, you can assume that the shares are numbered like y 1 till y t. Okay. So, we have got y 1, y 2, y 3 and so on till y t, and the corresponding x 1, x 2 and so on till x t. So, what will these collaborating parties do? These collaborating parties can apply the Lagrange's interpolation technique, right, and can try to find out a polynomial such that this polynomial should essentially fit all these t points, right. Now, you see that if your t is actually equal to L, what we have seen previously, then there is exactly one such polynomial of degree less than equal to t minus 1, right. So, that is exactly what the collaborating parties do. They essentially combine such that the objective is essentially now to deduce the constant term of the polynomial, but for that first of all we need to compute back the polynomial, right, because what the collaborating parties have is only the shares, right. The collaborating parties, if you see the collaborating parties, they have got x 1, y 1, x 2, y 2 and so on till x t comma y t, right. So, from there they actually apply the Lagrange's interpolation technique, okay, Lagrange's interpolation technique to obtain the value of the polynomial a x, right. And if they know the corresponding polynomial a x, then they know that a 0 is the secret of the polynomial, right. Is it no, right. So, therefore, if you know that when the polynomial was constructed by the dealer, right, if the dealer had ensured that in that polynomial, okay, in that polynomial whatever you say a x or b x, okay, in that polynomial your t was adjusted or rather L was adjusted such that it is exactly equal to t, then by the first lemma you know that there is exactly one such polynomial for which this holds, right. And therefore, the Lagrange's interpolation technique should be an efficient way to compute back the polynomial and hence the secret, right. So, that is the basic principle of the secret sharing scheme. So, therefore, being you know that so what the users do essentially is apply the Lagrange's interpolation technique and compute this, that is it takes all the y i's and compute x j minus x divided by x j minus x I not equal to j and j varying from 1 to t and I varying from 1 to t, right. That is what the users can do, right. And you know that your t is actually when the dealer had created this t is equal to L. So, therefore, this is actually there is only one such polynomial for which this fitting holds, right. So, actually the users or the collaborating parties do not need to calculate this value, then what they want is they only want the secret a 0, right. So, therefore, what they actually want is only this y I, you can actually plug 0 here and you know that it is x j divided by x j minus x I. So, what the collaborating parties want is only this, right, that is the corresponding secret. So, are we convinced that the collaborating parties will be able to calculate back the secret? So, let us consider one example. Okay. So, let us consider a small example. So, you see that in this example n is chosen as 5, that means there are 5 shares which are created and we want to ensure that if 3 collaborating parties combine, then they should be able to retrieve the secret, right. So, therefore, consider this example where there are n is equal to 5 and I want t should be equal to 3 in this threshold scheme. Okay. So, what the dealer does, so first the dealer has to create the polynomial, right. So, the dealer chooses a p which is a prime number such that p equal to 17 and chooses some xi's values. Okay. So, let us take the xi values are exactly equal to like 1, 2, 3, 4 and 5. Okay. So, that is this x1, x2, x3, x4 and x5 which is equal to 1, 2, 3, 4 and 5. Okay. So, suppose the secret which I want to share is the value 3. Okay. So, what the dealer does is the dealer chooses secretly the coefficients, say a2 is equal to 15 and a1 is equal to 14. So, you note that since t is equal to 3, what is the degree of the polynomial? It is t minus 1, so it is 2. Okay. So, therefore, the polynomial's nature will be like a0 plus a1x plus a2x square, right, and I know that a0 is what? A0 is the secret. So, what the dealer needs to do is that he needs to randomly choose a1 and a2. Okay. So, let this be the secret choices for a2 and a1. Okay. So, let a2 be equal to 15 and a1 be equal to 14, right. So, therefore, the polynomial which the dealer chooses is ax equal to 15x square plus 14x plus 3. Okay. And it needs to create all the shares. So, therefore, the dealer actually creates the shares in this fashion. The dealer creates the shares by computing y1 equal to a1, y2 equal to a2 and so on, y5 equal to a5, right. So, therefore, if you just plug in these values and you check, it will be equal to like 15 and this value will 6. The details are here. So, therefore, you see that the shares are y1 equal to a1 equal to 15, y2 equal to a2 equal to 6, y3 equal to a3 equal to 10, y4 equal to a4 equal to 10 and y5 equal to a5 equal to 6. So, these are the corresponding shares which are being created. So, now what we have to understand is that we have to see that if, for example, these 3 shares are revealed like 15, 6 and 10, then it actually gives me this value of 3, right. Or if any, that for that matter, if any 3 players combine here, they should be able to compute the value of 3. So, how many such 3 players can you choose? Out of 5, any choose 3. So, 5 choose 3, right. So, let us see the first 3 shareholders, for example, combine. So, in that case, they will actually apply the Lagranges interpolation formula over there. So, you see that if you see the first 3 members were 15 and y3 was equal to 10. So, there were 15, 6 and 10 which are being revealed. Suppose these are being given to the collaborating parties, right. So, 15, 6 and 10. So, if these 15, 6 and 10 are revealed, then what the user will do will apply, or these collaborating parties will apply Lagrange's interpolation on these 15, 6 and 10, right. So, therefore, if we apply Lagrange's interpolation on 15, 6 and 10, the polynomial is as shown here, that is, it is 15 into 2 divided by 2 minus 1 into 3 divided by 3 minus 1 plus 6 into, so 1 by 1 minus 2 plus 3 into 3 minus 2 plus so on. So, you see that this is given by this, right, that is, you know that for the general case this was the polynomial yi xj divided by xj minus xi I not equal to j and j equal to 1 to t and this is I equal to 1 to t. So, in our case t is equal to 3, right. So, if t is equal to 3, it is y1 and then you are doing a product the product is xj minus xi, okay, plus y2, again this product xj divided by xj minus xi plus y3, again this product xj divided by xj minus xi, and you note that this is what, I is 1. So, it is x1, this is x2 and this is x3, right, and you note that here j is not equal to I. So, that means j is not equal to 1 here, j is not equal to 2 here and j is not equal to 3 here, right. So, that means this is equal to y1 into, so what is the corresponding value of your j here? It can be 2 here because it is not equal to 1. So, it is x2 divided by x2 minus x1 multiplied by x3 divided by x3 minus x1 plus y2, and again here x1 will come and similarly x3 will come. So, it is x1 minus x2 into x3 minus x2 plus y3, this is x1 x2 and here your x1 minus x3 and x2 minus x3, right. So, therefore, if you see this and you just plug in the corresponding values of your x1 y1 x2 y2 x3 y3, which are nothing but what were the values? The values were this value was 1 comma 15, this value was 2 comma 6 and this value was 3 comma 10. So, if you plug in these values then you get this, right, you get this value, that 15 into 2 by 2 minus 1 into 3 by 3 minus 1 plus so on, right. So, therefore, you can see immediately that A0 is indeed equal to 3, right, this 37 mod 17. So, therefore, that is equal to 3, right. So, all these computations are modulo 17, that is modulo p. So, therefore, you see that you indeed get the value of the polynomial as it is shown over here. Now, therefore, now what we are essentially concerned is what about the security analysis, that is, if suppose lesser number of people combine than t, then what is the information leakage, right. So, what we have found out that is that if out of these n people, if t people combine, then they know the secret, right, but if suppose if less than that combine, then what happens, okay. So, for example, if you know that there are these things like if there are, so you know that a polynomial, if there are t members, then this is the corresponding polynomial, right, yi xj minus x divided by xj minus xi, I not equal to j and j equal to 1 to t, I equal to 1 to t, this is the corresponding polynomial, right. But suppose the number of colluding parties is actually, say, suppose t minus 1, even 1 less than that, right. So, therefore, the corresponding shares will be x1 y1 and so on till xt minus 1 and yt minus 1, right. So, they will apply a Lagranges interpolation formula on this, but note that they also know that the degree is t minus 1, right. So, how many such polynomials will exist, right. So, you know that by lemma 1, if there were L such members, right. So, then the number of polynomials was given as p to the power of t minus L, that was the first lemma, right. So, there were p to the power t minus L polynomials which were possible, right. So, therefore, if you have at least this L to be equal to t minus 1, okay, or you know that if this value, I mean you know that if this value is lesser than this, that is just what is said to be equal to L, then there is more ambiguity because there are larger number of polynomials which are possible, okay. So, being more precise, you see that suppose there are m shareholders who want to reconstruct the secret where m is less than t, Okay. So, without loss of generality again, assume that the shares are y I, where I varies from 1 to m. So, the shareholders know that a secret is the constant a0 of a polynomial of degree less than or equal to t minus 1. So, that is known essentially to the shareholders as well. So, which will satisfy a of x I equal to y I, but they do not have all the t shares, but they have only m shares, and you know that m is lesser than t, right. So, therefore, what is the information leakage or what is the knowledge that is leaked of the constant? That is the question that we are concerned with, right. So, therefore, however, we have the following result which follows actually from the first lemma. The result says that for any s dash, for any secret for that matter, there are exactly p to the power of t minus m minus 1 polynomials, okay, of this form of degree less than t minus 1, such that for all these m values this relation is satisfied. Why? Because in this assertion follows by using the fact that L is equal to m plus 1 in this case. Okay. Why m plus 1? Because any s dash you choose, right. So, any s dash you choose, you are applying the Lagrange's interpolation formula on this as well as on this, these m values. So, there is m plus 1, right. So, that is your L is equal to m plus 1 in this case. So, if you plug in L equal to m plus 1, right, and you know that lemma 1 says that there are p to the power of t minus L such polynomials. So, that means if you plug in L equal to m plus 1, there are p to the power of t minus m minus 1 polynomials which are possible, right. So, what did the first lemma say? The first lemma said that there are exactly p to the power of t minus L polynomials. Okay. So, for I mean where all these values are satisfied for all these L values, right. So, therefore, now in our case this has to satisfy for all these m cases as well as for the constant which you are choosing for any s dash, right. So, that means it is for m plus 1 values, right. So, therefore, the number of such polynomials is exactly equal to p to the power of t minus L, and L is equal to m plus 1, right. So, that is p to the power of t minus m minus 1 such polynomials. Okay. So, therefore, there are exactly p to the power of t minus m minus 1 such polynomials possible, and that is for any secret s dash which you are choosing. There exists p to the power of t minus m minus 1 polynomials for which y or rather y I is equal to a of the polynomial you are applying x I for all i's varying from 1 to m. Right. So, therefore, you see that if you set your t to be equal to, so there are how many such possible cases here? Right. So, if you set now your t to be exactly equal to m plus 1, okay, or rather m is equal to t minus 1. So, then there are how many polynomials? That is exactly one polynomial. So, that means in that special case for any s dash there is one polynomial for which this result holds, right. So, which means that for any s dash you can select, for any secret which you choose, there is one such polynomial, right. So, that means these m shares where m is equal to t minus 1 is not revealing any information. You see that, because whatever be the secret value, there exists one polynomial for which the relation holds for these m points, right. So, therefore, since therefore, these x 1 x 2 and so on till even these t minus 1 values, or rather these shares are not leaking any information whatsoever about the secret, right, because whatever secret you can think of all from 0 to p minus 1, there exists one polynomial for which this matching holds, for which the relations hold, right. So, therefore, this is not revealing any information whatsoever about the secret, which is the actual secret. But if you make this t, or rather make the value of m to be equal to t, then there is only one such polynomial for which this relation holds, okay, and therefore, the constant of that is giving you the secret. Okay. So, that is the basic analysis. So, that means that the assertion shows that with m less than t, so obviously if the sharing is even smaller, then the information leakage is even less, and therefore, this shows that with m less than t shareholders, all the values of the secret are possible, right. So, you can consider some points to think on. For example, you can reconstruct the secret in the example from any of the 3 shares, that I mean I have just considered the first 3 shares, you can choose any 5 choose 3 shares. Okay. And other thing which you can try is that to construct or reconstruct the secret from 2 shares and convince yourself that all values of the secret are indeed possible. Okay. So, some of the references which I have used is the Buchman's book Introduction to Cryptography, and also the actual paper which was written by Shamir in 1979, says that how to share a secret. Okay. It was published in Communications of the ACM. So, in the next day's class we will take up the topic on tutorial on network protocols. So, we will first of all consider that all of the things what we have learned together, and or at least some of them, how to essentially apply them to develop a secured protocol, okay, secured protocol over the network.